All right, hey everyone, good morning or good afternoon, whenever you're watching this. This is going to be lecture 21. We're going to be wrapping up the increase in stress. So remember, this is that delta sigma z, and this is going to be due to the different types of loading at the ground surface. So usually what we are looking at here is we have our new total stress, and this is going to be equal to our increase in vertical stress plus our in situ initial vertical stress. And we found out how to find this. This is that whole summation of unit weight plus H, the soil layers. This is what we've been finding so far using Boussinesq, using 2-to-1 method. Now today we're going to be looking at another application of Boussinesq, actually two other applications of Boussinesq, which is the Newmark chart and the trapezoid embankment thing. All right, so this is the same slide as before. I just crossed some stuff out as before, or the same schedule that I talked about previously. I wanted to bring on your radar at least that this is a typo here. Your notes are different, but this is going to be due this week. So tomorrow, if you're watching this on Thursday, which hopefully you are. Should also note here that this is a wrong date. I don't know what happened there. This is April 18th that you're watching this, hopefully. So no labs this week, done with labs, but we still have a quiz that's going to be due next week here. Your homework 4 is posted now, and that's going to be due next week. And then your lab number 9 is due next week too. So these are all should be on Sunday by midnight. So please keep up to date with those. These here, these will be both due on Friday. So lab number 7 is actually this week, which will be the 19th. And I will update those before I post them. All right, so remember we have been talking about the increase in vertical stress. What is going on? The increase, no idea what that is. Anyways, increase in vertical stress. This is for chapter 10 in your Holtz and Kovacs textbook. But then I've also uploaded the DOS chapter 10 textbook as a PDF, and it was back on last week's thing. So please use that as a reference there. Just to recap what we've been talking about so far. We've been talking about the point load, the Boussinesq ones that are all here. Actually, well, all of these are Boussinesq methods, which is based off of a theory of elasticity. And these are the equations that associate it, and then the tables. Because remember, we have those influence factors that make the math a lot easier for us. So remember to keep track of the units of the loading that is given to you. These point loads will always either be in a pound or a kilonewton, right? Some type of force. These line loads would be a pound per foot or a kilonewton per meter. So that's line coming in and out of the paper, out of the little 2D area. And then the strip loads would be like pound per foot, something like that. So pound per square foot. And then of course the rectangular loaded areas, these are 3 dimensions there. So it'll be pound per square foot or kilonewton per square meter. So please just keep track of those on your exam. All right, so what we're going to be talking about today is a special application of Boussinesq's theory, and this is under an earth embankment. And we've kind of talked about this in the past, but a lot of engineering principles and theories are developed based off of the more empirical approach, meaning that it's actually like the application in the field. So this is one of those cases where we see a lot of earth embankments or earth dams or something added to the surface, and we would need to determine the increase of stress behind that. So this is really popular for dikes, or like we see at Lake Okeechobee. That looks something like this. And we have this fill material with those cutoff walls, like the seepage thing that we had talked about before. So we need to understand the seepage or the flow rate behind that, but then also the increase of stress. If we had a layer down here, that might have an issue due to that. So this type of shape is very common in geotechnical engineering, pyramid shape, and that's just because we can stack soil up, but in order to ensure that it is not failing, we would need to have it at this 2-to-1 slope or 3-to-1 slope, some type of slope, So we can still get the height achievement or the elevation change, but then also not have any type of failure or landslides. So this type of shape here, remember this is coming in and out of our screen. This is a 2D plane representation of it. So you take a cross section of it. No idea what happened there. And the increase in vertical loading underneath this would be something that we would need to consider. Now, we also see this in terms of embankments coming up like to a bridge approach. You can kind of outline and see this here. If this is our soil layer here, we see this again, trapezoidal increase of soil or height. That is going to cause some type of increase of stress. So we know from structural loading, right? Like this P or something, this column load is going to be taken from the dead loads of the object, the wind loads, the gravity loads, the seismic loads, something from the structural engineer. And this is going to be applied over a cross-sectional area. And sorry, this is another typo here. This should be feet squared in the units that we're using here. Now we know that this is going to cause an increase of stress moving this way, and that's going to be producing this delta sigma z that is changing with depth. So the stress applied at the surface, just to recap this, is the force divided by the cross-sectional area. Now, when it comes to an embankment, we have this type of trapezoid, but the stress applied is not from a structural loading, but rather it's from the soil density. So we are going to have, let's just say it's a one meter thick of it. This stress applied at the ground surface is going to be due to this density times h, and that h is going to be the height of our embankment here. So how could we find the stress increase due to loading under this embankment at a depth z? So this is going to be in the middle. So what we assume though is Boussinesq actually takes this, if it's in the middle, we take this and we look at a two-dimensional cross section, and then we're going to multiply it by 2. So this is where Boussinesq theory comes in, where if you look at your tables, you'll see a figure that looks like this, where the stress applied at the surface, this Q naught, is the density of the soil times the height of the soil, two things we can control, one through compaction, one through construction. And then based off of the dimensions of this B2, B1, and the corresponding Z here, then we can estimate the point increase of stress. So what's important is when you see this figure, this is the analysis for half an embankment. So if we are doing this in the middle of the embankment, then we would have to multiply this by 2. And we'll show some examples here in a second. This is the math that shows it. As you can see, it's just summarized again through a beautiful little influence factor where we have the chart that encompasses all of these geometric parameters. This is going to be table or figure 10.15. So for a full symmetric embankment, if this is in the middle, then this increase of stress, again, this is only due to half of the embankment. So if we had another half of the embankment on the other side, then we'd have to multiply this by 2 to get the total embankment increase of stress. So this is that beautiful table here. Remember here, this is an important note, like the edge or half of the embankment is going to be Q times I2. If you want the full embankment under the center, then that's going to be delta sigma z 2Q times I2. So same influence factor here, you just multiply it by 2. How we would read this, B1 divided by Z, you can see this is the flat portion. So that's going to be those contours, and then B2 divided by Z, that is going to be on the x-axis. The I value that we want, this I2, this is going to be the y-axis here. So let's say we have a B2 divided by Z of 1. And then let's say we have a B1 divided by Z of like 0.5 or something. So that'll be this section here. You would actually use a straight edge and not me on this little laptop to try to draw a straight line. We would see where it intersects with that contour. And then again, drawing a perpendicular line here, that would be our I2 value. And we'll show some examples of this. These types of graphs are much, much easier than just applying all the geometric properties here in this equation in the bottom right. But you're welcome to do that if you want. If you love math and you love the potential of doing little errors in your calculator, then feel free and use that math equation. Okay, so for this example, what is the increase of vertical stress at 6 meters below the center of the embankment? So we read this, we see center. This means we're going to be multiplying our increase of stress by 2. Because remember, all of the Boussinesq theory is assuming you are only using a half trapezoid. So if we're in the center here, then we know that there's an actual equal trapezoid on the other side. So that contribution is going to be 2 times what the one that we're calculating. Okay, so we see a bunch of geometry properties here. The H is going to be 3 meters. We see a soil density in some horrible units of megagrams per cubic meter that we'll work through in a little bit. And then we can see right off the bat, our B1 is going to be 5 meters, right? That's going to be this one. And then we're going to have to do a little bit of math to find our B2 because we're given the slope, but we are not given this actual parameter here. So let's start with the density first. So to find this Q value, the Q being gamma times the height. To find our gamma, since we're given density, we know that density times gravity is going to be our gamma. But when we do these units, it's horrible, 19.6 megagrams per meter squared per second squared. But this is where the kilonewton comes in. So remember, 1 Newton is equal to 1 kilogram meter per second squared. So 1 kilonewton is equal to 1 megagram meter per second squared. So we can put this little guy right here and plug that in there. And then boom, we get our density or our unit weight being 19.6 kilonewtons per cubic meter. So that's going to be our gamma. So the Q is going to be the gamma times the height. Our height is 3 meters right here, given in the problem statement. So our Q in our equation is going to be 58.8 kilonewtons per square meter. Okay, kilonewton per square meter, that makes sense. This is stress. Remember, even though we're seeing a 2-dimensional thing here, this is technically something that extends out of the paper. We're looking at a unit of depth or a unit of length of this embankment. So that's where that meter square comes from. Okay, so for our B1, that's given to us as 5 meters. That's nice. For our B2, we're going to have to calculate this. Now, we know that it's going to go over 2 and down 1. That's what this slope is telling us here, this 2-to-1 slope. So if we are going over 3 meters, that means we are going down 6 meters. So we go over 2, sorry, other way around. If we are going down 3 meters, that means we have to go over 6 meters to achieve that. So the other way to think of that is B2. So remember, we're only going down 3 units. So 1, 2, wait, yeah. So 1, 2, 3. So we're going down 3 meters. So for the first one, we go 2, 3, 4, 5, 6, and it's not actually drawn to scale, but you guys know how triangles work. So you could use sine and all that stuff if you'd rather do that. But the whole end of the story is that this unit is going to be 6 meters over. Okay, so we have that one so far. We know our depth Z is going to be 6 meters as well. So we then need to find those 2 geometric parameters. We have B2 over Z, which is 1, and then B1 over Z, which is 0.83. So let's look at our table here now. So our B2 over Z, that is going to be the x-axis. That's going to be right here on our 1. And then B1 over Z, that's going to be 0.83. So somewhere in between here. So this is 0.8, this is 0.9, and we have to keep just shy of that 0.8 line. Now, this is where the assumptions, or sorry, the approximations just come in out the wazoo, right? We're not going to be able to tell exactly what is 30% or 3/10 of, or 0.03 between these 2 lines. So we're going to interpolate that and hope that that is kind of that midway or that 0.3% range of it. Regardless, we're going to read that over and we see our y-axis here. This is going to be that I2, this influence factor, and we're at 0.4, 0.1, 0.41, 0.42, 0.43, 0.44. We'll just say that's close enough to 0.44 right there. So our increase in vertical stress due to half of the embankment is going to be this Q times I2. So remember, our Q is this. This is for half of the embankment. But since we are looking at the full embankment, we have to multiply this by 2. Another prime example, put a little star in this top right here and just put like FE. Remember this, because this is one of those things where it'll be a full embankment problem. You're going to go through all these steps and boom, that answer 26 will be on your FE. But you would need to know to multiply it by 2 since we have a full embankment, since we have our figure looking like this. So full. So up on the other side and down on the other. So this would be the answer for this one. Now let's look at this one. We have just a triangle for whatever reason. Maybe there's like some retaining wall or something here that's able to hold it up, and we just have this half retaining wall. So let's look at the same thing. We have the same density of 19.6 kilonewtons per cubic meter, same depth, 3, but now the width is going to be 6 meters, and this Z is going to be 6 meters below. So what is the well, I guess I already found that there. So let's look at the geometry here. So remember, this is B1 and B2 is based off of this trapezoid, half trapezoid looking figure. So for our B2, this is going to be the sloped side. That's already given as 6 meters. But our B1, since there's no flat side of it, this B1 is going to be equal to 0 meters. Now our H and our Z are given already. So Z is going to be 6 meters, H is 3 meters. So for this, then we would look for the 6/6. So this is still that depth ratio B2 over Z. That's going to be 1. But now for this 0/6, this is going to be our 0. So we'll read this up onto this very bottom contour and then read over, and we have an influence factor of 0.24. Now, in order to find the increase of vertical stress, this is our Q times that. So same Q because it's 19.6 times 3, and then times this influence factor of 0.24. Now, the question is, do we need to multiply this by 2 or not? We do not. So this is just as is. This is the answer. Sorry, let me go back. The only time, if we were to have to multiply it by 2, it would be if we had a pyramid or something. Then that's when we would multiply it by 2, and only if it was symmetrical. If the slope, the downslope on the opposite side, if it was a different angle, then we would just have to find each one independently and then add them together. So you can only multiply this delta sigma Z by 2 if it is symmetric through that center line, meaning that we are looking for the point in the center of this whole thing. This one's on the edge though, so we're good. We don't need to multiply it by 2, and this is the answer. So what would happen if we wanted to find the stress under the corner of an embankment? So like, let's say over here instead. Remember the whole Boussinesq theory, those tables, those charts and everything, that was all assuming it was under the center or under the edge of the this zone. So remember, something that looks like this, meaning the edge of the flat or the height section, the rectangular section, not the triangle section. So what would happen, or how could we still use Boussinesq to solve for this delta sigma Z if it's over on the outskirts underneath the triangular portion of our full embankment? So what we would do is, much like we did last week in class, where we had to add a fake or a pseudo area, we're going to have to do the same thing. So what we can do is we can pretend that this entire thing looks something like this, where we have a rectangular mode, and that is now equal to the same geometric setup that the Boussinesq equation is set up for. But now we've added this little fake triangle here. This is that fake one just to help with the analysis. So we're going to have to subtract that out of it to get the actual true delta sigma Z. So the true part, looking at the top, so this is the actual, we have to, we're going to say this is equal to our fake or our pseudo one minus the thing that we added there. So the full embankment, just so we can help with the math, and then we're going to subtract out that delta sigma Z due to this added triangle. So this is, this requires, it's the same steps. You would just have to find an I2 here for this one, and then you'd have to find a similar I2 here. So then you would find a delta sigma Z, and this is going to be our like fake And then you would here find the delta sigma z. This is our like pseudo added one. And then the real delta sigma z is going to equal the delta sigma z fake minus the delta sigma z for the added, something like that. So these would have their own, yeah, this one down here would have its own B1, B2. This one right here would have its own B1, B2. The stress, though, would be the same because this Q would still equal times H. This Q would still equal gamma times H. This H, though, is going to be the same, and we're assuming that the density is the same for each one. So the Q can actually be used again, but those geometric parameters you'd have to change. Okay, so that is the stress due to an embankment. Let's look at another thing. Let's say we have some irregular shapes off center. Remember, we have a Boussinesq equation and table and charts and all that stuff for a rectangular loaded area. We can also look it up for a circular area too. Let's say we have something that looks like this, right? Some type of footprint of a building where, it's like a rectangular, half rectangular point. And then let's say there's some existing structure or tunnel or something where we would have to actually find the delta sigma underneath this point. That's, not under a corner, not under, you could divide this up, but it would just take a really long time. So we know for a rectangle, we can find center or corner, but then you'd have to divide it up and do all these things just to find that of all these fake or real areas and subtract them out like we showed last week in class. So in general, we know that the increase in vertical stress is going to be equal to this Q, the stress at the surface, times this influence factor. In this case, we're given a uniform load at the surface. And this, again, this is bird's eye or plan view here shown here if you haven't noticed that yet. So we're looking down at the layout of the foundation. We know that this I value is some influence value less than 1. So what the Newmark chart does is it applies the Boussinesq equation to get an approximate influence of any shape under any point. And it uses Boussinesq theory, and it looks kind of trippy here in a little bit, but it's a really useful tool to estimate this influence factor I. So for the Newmark chart, again, it's a method to graphically determine the influence or shape of any shape under any point using Boussinesq. And what it does, and it looks like this, and it looks like some Star Wars stuff going on, but this is a scaled representation of this influence value. And that point there that we have in the center is the point at which we want the increase in vertical stress at, or we care about the increase in vertical stress at. So first, it sets the scale of the chart. So this is the important thing. That scale is needed for depth. So this is going to be the Z depth. So this point A to B, that's going to be the Z depth of it. So how we find this delta sigma Z is we have that Q value from the loading. But now what we're going to do is multiply this by the influence factor of the chart or influence value. So each chart that you see will have a set distinct influence factor that's already predetermined based off of the scaling and how the chart was drawn. And then what we do is we superimpose the surface area of our footing or our building footprint or whatever we have at the ground surface. We superimpose that scaled to this, or we superimpose it over the Newmark chart. So if we have something like this, and we know these dimensions are 40 feet here, right? 40, 60 feet. So we have the scale, everything is drawn to dimension. This AB is the depth of interest scaled with the outline. So let's say we care about 10 feet, or let's just keep it simple. Let's say we want to know the increase in vertical stress underneath the footing at point O dot, or O apostrophe, at a depth of 40 feet. So since this depth is 40 feet, or sorry, since that dimension is 40 feet, we would have to scale this entire footprint to equal, this would be equal to 40 foot, this A to B section here. So I'm sorry, I guess in my example, I said 60 feet. So if it was 60 feet, then this section here from A to B would be 60 feet, and we'd have to scale everything accordingly to it. We would then count the number of cells covered in the scaled area. And so these cells, let's look at it here. Let's see. Well, we can clearly see that these are fully covered, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So we have a full 21 cells covered, but we're looking for the total cells. So maybe we can call this 22. These two combined 22. These two combined 23. And we'll just go ahead and round up and say that one's 24, that one's 25. These three are going to be 26. These right here kind of close to 27. Let's just say the next one, we can just put one other one there. So 28. All right, maybe these down here also 29. Okay, this is 20, 30. And then we'll just say these two here for 31. So 32. So the whole thing is like we are approximating, and since you have these geometric shapes overlapping these other like kind of scaled rectangular shapes, it's not going to be exact. So out of the total number of cells covered, you usually round up and be conservative. This total numbers of cell covered we'll say is 32, meaning our increase in vertical stress is going to be the Q, which is of the ground surface, times this influence value of 0.005. Remember, that is the thing that is set by whoever drew the chart, and then times 32. So in this case, if our Q value was 250 kPa, so 250 kPa times 0.005 times 32, boom, that's 40 kilopascals. That's going to be the increase of depth at a Z of 60 feet. So very 50s, very 40s, I guess. I don't know. Very rough estimate, but it's a good quick estimate. Thinking back in the day before you had, computers to really work through this stuff, you could print out or even like draw these Newmark influence charts and then just scale your footing using paper to whatever we need to be, overlay it. And this allows us to solve for a bunch of different points as long as that center point 0 or the point that we care about is with respect to and drawn to scale with the location of interest. So I do want to point this out there. So again, like this point being 0.0 right here. So that means that this is a scaled 20 meters away because this dimension is 60 feet or 60 meters. So this is 60 meters. So now we've set the entire scale for it. And so we would need to ensure that everything is plotted on our chart, drawn to scale, just like the same proportions that this is. So that is embankment and then Newmarks. Embankment, for sure, I've seen it on the FE. Newmarks, it's a helpful tool. I don't know if it's on the FE at all. It's kind of sketchy, right? Because it's up to the interpretation of actually how many area or how much surface area it takes, how many cells you cover there. So we have these now. This is the whole gamut of increase of vertical stress. So increase of vertical stress due to point load, vertical line load, horizontal line load, vertical strep. All of these here you can find in your DOS chapter 10 textbook pages that I've posted on Canvas. You can download and keep those and bookmark these. Print them out, keep them as a notebook just in case you might need this future in your career. And again, though, that this is to find this increase in vertical stress. So this is due to the loading. And what we might see is that this loading can actually change over time. And so we have our in situ vertical stress, and then this new increase in vertical stress might change over time due to different incremental loading. If we think about different types of construction, right? We don't just put a building on it right away. We're going to be loading it over time with this dead weight as the construction occurs. So next class, what we're going to talk about is a specific type of problematic soil that we see a lot of in Florida, and that's going to be our organic and peaty soils where we have high compressible. And one of the things that we can actually do is utilize this increase in vertical stress to induce settlement before we put our structures on it. So this is a process called surcharging. I'll go over that, and we're also going to talk about soil sensing too. So very quick lecture here. You can watch it super, super slow or super, super fast. Watch it again. But these two things, the embankments and the Newmark chart, these are going to be important for you to know on your exam 3. So please make sure you get an understanding of how to read them and how to apply those charts. For the Newmark chart, of course, on the exam, it's going to be given to you. You're not going to have to draw anything. So you already have the influence factor, and you're not going to have to print anything out for scale. So, or use AutoCAD. So you'll be fine there. You just need to make sure to know how to read the Newmark chart. All right, next class, sorry, not this here. We're going to be talking about problematic soils, compressible soils, and how to fix them in the real world, especially here in Florida. All right, guys, enjoy your weekend. See y'all next week.